In the next 30 minutes, you will understand policy gradients. This is the core algorithm powering the alignment of ChatGPT. Think about it. Training a model on a dataset is easy. We call that simple fine-tuning. But what about abstract goals? How do you train for goals like be more helpful or write safer responses? Here's the thing. You can't just write a loss function for that. You need to give the model a score, a reward. And here's the problem. That reward signal is a black box. Look at this diagram. You have your agent, your policy, and it sends an action out into the world, into a black box environment. This could be a human or another AI judge. And what comes back? Whether it's from a human or an AI, you just get a single number back. That's it. And this is the critical part. You cannot backpropagate through a human's opinion. As you can see in this updated diagram, the path for gradients is just broken. It hits that black box and stops dead. This means standard gradient descent is completely useless here. This is the exact problem policy gradients were designed to solve. They let you optimize a policy directly, even when the reward function is a complete mystery. We are going to build this entire concept from the ground up. By the end of this video, you will understand. First, the policy gradient theorem. Now, don't get intimidated by this big formula on the screen. This is the mathematical key, the trick that unlocks the gradient for a black box reward. Next, reinforce. This is the simplest, most intuitive policy gradient algorithm. It's the perfect place to start. Then we'll move on to actor-critic methods. This is how you slash variance with a learned baseline to make your training way more stable. And finally, proximal policy optimization, or PPO. This is the modern standard, the algorithm that uses KL divergence constraints to get the job done reliably. Let's start with a simple goal. Imagine this ideal scenario. We want to find the input, let's call it x, that maximizes a known reward function, r of x. For our example, let's say the reward function is r of x equals negative x minus 2 squared plus 10. You can see it on the screen. It's just a simple, clean parabola with a peak. Now, if you know the formula, this is a solved problem. The solution is just gradient ascent. Here's how it works. First, you start at a random point. Let's just pick one, say x equals negative 2. Second, you calculate the gradient. The gradient tells you the direction of steepest ascent. It's the fastest way up the hill. At our point, x equals negative 2, the gradient is r prime of negative 2, which is negative 2 times, well, negative 2 minus 2, which equals a steep 8. It's telling us to move right and fast. So third, you update your position. You take your old position and just nudge it a little bit in the direction of the gradient. The formula is simple. X new equals X old plus some learning rate, let's call it alpha, times the gradient. So in our case, that's negative 2.0 plus our learning rate of 0.1 times 8, which gets us to negative 1.2. Closer to the peak. Here's what just one step looks like in code. It's really straightforward. We define our reward gradient function, which is just the derivative, negative 2 times x minus 2. We set our starting x to negative 2.0 and a learning rate of 0.1. Then we perform one step of gradient ascent. We call our function to get the grad, and then we update x. X equals x plus learning rate times grad. And if you print that out, the gradient is 8, just like we calculated, and the new x is negative 1.2. This works perfectly. We just repeat this process over and over, and we'll find the maximum. Easy. Now for the critical change. Imagine you do not know the formula for r of x. It's a complete black box. All you can do is queries it. You can pick an x, you can feed it into the box, and the box will spit out the reward. But you have no idea how that number was calculated. You try a query. You give it x equals 4. The box returns r of 4 equals 6. Okay. You try another one. Query x equals 0. The box returns r of 0 equals 6. How do you find the peak now? You can't calculate the gradient. Standard gradient ascent is completely impossible. You're flying blind. This is the exact situation we face when aligning large language models. Let's map our simple problem directly to the world of LLMs. You can see this in the table here. our simple input, x, that's the LLM's parameters, theta, billions of them. The reward function, r of x, that's a reward model that scores generated text, r of y. And finding the best x is the same as finding the best parameters, theta, to generate high reward text. So here's the flow. The LLM parameters, theta, are used to generate some text, y. That text then gets sent to the reward model, which acts as our black box. It returns a single score. Maybe r of y equals 0.9 if the text was helpful, or 0.1 if it wasn't. And here's the absolute core of the problem. You cannot backpropagate a reward score through text generation and human judgment. The path is broken. The gradient just stops. And this sets up the central problem we have to solve. How do we update our model's parameters when we can't backpropagate through the reward?
So, how do we solve this impossible problem? The answer is the policy gradient theorem. This is the mathematical foundation for everything that follows. Now, on the screen you're seeing a big, scary-looking formula. Gradient of j of theta equals an expectation of a sum of gradients of log probabilities times a reward. Whew, I know this looks complex. If you've seen this before, you might have just accepted it as magic and moved on. Not today. You are going to understand exactly where this comes from. Let's build this as a story. First, we'll explore the naive approach, which is a total dead end. Then, we'll meet the hero that saves the day. Let's start with the naive approach, a dead end. Our goal is simple: maximize the expected reward. We write this as j of theta. Mathematically, it's just an integral over all possible trajectories, tau. You can see it here. J of theta equals the expectation of the reward, which is the integral of our policy probability, pi theta of tau, times the reward for that trajectory, r of tau. Step 1. Take the gradient. To perform gradient ascent, we need the gradient of our objective. So we just slap a gradient symbol on the whole thing. The gradient of j of theta equals the gradient of that entire integral. Simple enough, right? Step 2. Swap the gradient and the integral. Now, assuming we can just move the gradient inside the integral, and since the reward, r of tau, doesn't actually depend on our parameters theta, we get this expression. The gradient of j of theta equals the integral of r of tau times the gradient of our policy, pi theta of tau. This is a dead end. The expression is mathematically correct, but it is computationally useless. Why? Because to estimate an integral from samples, it must be in the form of an expectation. It has to look like the integral of some probability distribution p of x times some function f of x. That's the only way Monte Carlo estimation works. But look at our formula. The distribution part is the gradient of pi theta, not pi theta itself. We know how to sample from our policy, pi theta, but we have no idea how to sample from the gradient of our policy. We are completely stuck. Now for the hero of our story, the log derivative trick. This is a simple, beautiful identity from calculus. You've probably seen it. The derivative of the log of f of x is the gradient of f of x divided by f of x. If we just rearrange that a little bit, we get our trick. The gradient of f of x equals f of x times the gradient of the log of f of x. It's so simple. Let's apply this trick to our policy, pi theta of tau. The gradient of our policy equals the policy itself times the gradient of the log of our policy. Do you see where this is going? Now, let's substitute this back into our dead-end integral. Our gradient of j of theta becomes the integral of r of tau times, and here's the substitution, pi theta of tau times the gradient of the log of pi theta of tau.
By reordering the terms, just moving pi theta of tau to the front, something incredible happens. Look at this. The gradient of j of theta is now the integral of pi theta of tau times the quantity, r of tau times the gradient of the log of pi theta of tau. This is the breakthrough. The integral is now an expectation,
Our probability distribution, P of x, is our policy, pi theta of tau. We know how to sample from that. And our function, f of x, is just that whole term in the brackets. This means the entire integral is just an expectation. The gradient of j of theta is the expectation, when we sample trajectories from our policy, of the reward for that trajectory times the gradient of the log probability of that trajectory. That's it. We transformed an intractable integral into a simple expectation. And we can approximate any expectation just by sampling. The simplest possible implementation of this idea is the reinforce algorithm. So here's how the reinforce algorithm works. First, you initialize your policy network, pi theta, with some random parameters. Then you just loop forever. Inside the loop, you do a rollout. You generate one full trajectory, tau, using your current policy. Then you calculate the reward. You send that trajectory to the black box and get the total reward, r of tau. And finally, the update step. You calculate the score, which is just that gradient of log pi theta of tau term, and you multiply it by the reward. Then you perform one step of gradient ascent. Your new parameters, theta, become the old theta plus a learning rate, alpha, times the reward, times that score. The intuition here is so powerful. If you get a high positive reward for a trajectory, we take a big step to make all the actions in that trajectory more likely. But if you get a low or negative reward, we take a step to make those actions less likely. We're literally reinforcing good behavior. Let's make this concrete. We're going to apply reinforce to our simple 1D problem from Chapter 1. Okay, let's review the problem context. We're applying reinforce to that black box function from before. Our policy, pi theta, is a normal distribution. Our learnable parameter, theta, is just the mean of that distribution, mu. Our action, a, is just sampling a single number, x, from that normal distribution. Our reward, r, comes from the black box. Negative x minus 2 squared plus 10. And finally, the score, that gradient of the log probability term. For a normal distribution, this simplifies down to a beautiful, simple expression, x minus mu divided by sigma squared. So let's look at a single reinforce update step in Python. First, we import numpy. Then we have our reward function, which is our black box. We set our policy parameters. Let's say mu starts at negative 2.0, and we'll keep sigma fixed at 1.0 for simplicity. We also need a learning rate, say 0.01. Okay, step 1. Sample an action from the policy. We call numpy.random.normal with our mu and sigma. Step 2. Get the reward from the black box by passing our sample into the reward function. Step 3. Calculate the score function. This is just the formula we saw. Our sample, x, minus mu divided by sigma squared. Finally, step 4. Update the policy parameter mu. Mu equals mu plus the learning rate times the score times the reward. That's it. Now, for example, let's imagine we got a lucky sample. Let's say our policy, which is centered at negative 2, happened to sample the value 1.89. That's really close to the peak at x equals 2. The reward for this sample would be a massive $9.99. The score, or grad log pi, calculates to 3.89. And the update term, which is the score times that huge reward, is 38.82. This pushes our updated mu from negative 2.0 all the way to negative 1.61. The huge reward scaled our score, pushing our mean mu directly towards the peak. This simple mechanism, all enabled by the log derivative trick, is powerful enough to optimize incredibly complex systems. Okay, we have the reinforce algorithm. It's powerful, it works, but so far it's just been theory. It's been a toy problem. It is time to translate this algorithm into the real world of large language models. And in doing so, we're going to discover its critical hidden weakness. So first things first, let's build our Rosetta Stone, translating the language of reinforcement learning into the language of LLMs. Okay, here on this table, we have our Rosetta Stone. On the left, the RL concept, and on the right, the LLM equivalent. First up, the policy, pi theta. What is that? Well, that's just the LLM itself. The model is the policy, defining a probability over the next token. Easy enough. Next, the state, S sub t. That's just the prompt plus all the tokens you've generated so far. It's the entire context the LLM has at any given moment. So what's the action, A sub t? That's just the very next token you sample from the model's vocabulary. The trajectory, tau, is simply the complete response, the full sequence of tokens from start to finish. And finally, the reward, R of tau. This is a single score for the entire text, usually coming from some external reward model. With this mapping, that key term from our algorithm, you know the one, nabla theta log pi theta of at given st, that just becomes the log probability of the token you chose. It's a standard output from any transformer model. No extra work needed. Alright, let's see this in action with a step-by-step example. Our goal? Teaching an LLM to write better poetry. Step 1, the prompt. This is our initial state, S0. Write a haiku about robots. Step 2, the rollout. This is where we sample a full trajectory. The LLM takes the state and generates the first token, our action, A0, which is metal. Now the state updates to robots, metal. The LLM takes that state and generates the next token, A1, gears. The state becomes robots, metal gears, and so on, until we have our final trajectory, tau, which is the complete haiku, the sequence of words, metal, gears, softly, turn, circuits, and the rest. Step 3, the reward. Now we take this complete response, metal gears softly turn, circuits hum a new day's song, I am now awake, and we pass it to our black box, the reward model. Think of it as an AI poetry judge. It reads the whole thing and gives it a score. And it gives it a score of 0.9, a pretty good score. Step 4, the update. This is where reinforce does its thing. We use that single reward, R of tau equals 0.9, to update the probability of every single token in that sequence. The signal for the first word, metal, is the gradient of its log probability, times 0.9. The signal for gears is the gradient of its log probability, times 0.9. And we do this for every single token in the haiku. The final gradient is the sum of all these signals, which nudges the LLM to make this entire sequence more probable in the future. This process works, but it is incredibly inefficient. The reason is a classic problem in reinforcement learning: poor credit assignment. It's like giving one final grade to a big group project. Someone did all the work, someone else did nothing, they both get a B+. It's not fair, and it's not a good way to learn. Think about it. The reward R of tau equals 0.9 is for a dozen different decisions the LLM made. What if one part was amazing and another part was meh? For example, metal gears softly turn. Maybe that was a brilliant, creative line. It gets rewarded with a score of plus 0.9. But what about the last line? I am now awake. That's a bit generic, maybe a bit weak. Reinforce rewards that weak line just as much as the brilliant one, plus 0.9. And conversely, if the overall reward were low, say 0.2, the brilliant parts of the response would be punished just because they were part of a bad group project. This smearing of a single reward across the entire sequence creates a high variance, noisy gradient. The signal gets diluted. It's a slow, unstable, and extremely sample-inefficient way to learn. So reinforce works, but it's a brute force tool. To make this practical for something as complex as an LLM, we need a more surgical approach. The real problem here is the question we are asking. Was the final outcome good? Is the wrong question. The better question, the more precise question, is, was this specific action better or worse than what I expected to happen at this point? Answering that question is the key to taming the variance. Answering that question is the core idea behind our next topic, Actor-Critic Methods. Imagine you're playing a video game, and after a tough level you score 80 points. So, is that good? Well, it really depends, doesn't it? Let's look at scenario 1. If the average score for this level is only 30 points, then your score of 80 is excellent. You should strongly reinforce the actions that led to it. Whatever you did, do more of that. But now, Scenario 2. What if the average score is 95? In that case, your score of 80 is terrible. You should actively discourage the actions that led to it. You see, the raw score is far less informative than the advantage. How much better or worse you were than average. That is the signal we need. So here's the trick. Instead of scaling our gradient by the raw reward, r of tau, we'll scale it by r of tau minus b, where b is our baseline, our expectation. This gives us our updated policy gradient. You can see the formula here. The structure is exactly the same as before. But look at that highlighted part. Instead of the raw reward, we multiply by the reward minus our baseline. And the best part? This is a totally sound mathematical trick, as long as our baseline b doesn't depend on the specific action at we took. This simple change dramatically reduces variance by letting the algorithm focus only on the truly exceptional or truly terrible outcomes. Everything else that's just average gets an update signal close to 0. It's so much cleaner. So, this brings up the obvious question. What's the best possible baseline? A simple average won't do. We need a smarter baseline. We need the value function. See, the ideal baseline changes depending on the situation you're in. So the best baseline is the average expected reward from our current state, s sub t. This is called the value function, written as v of s sub t. It's the expected total reward if we start in a specific state and then just follow our policy. With this powerful new tool, we can define the advantage function. Check out this formula. The advantage, a of st at, is simply rt minus v of st. Or in plain English, advantage equals the actual reward you received minus the expected reward from this state. It's the measure of surprise. So if the advantage is greater than 0, that's a positive surprise. The outcome was better than you expected. The algorithm's response? Make the action that led to it, at, more likely. And if the advantage is less than 0, that's a negative surprise. The outcome was worse than expected. So we make the action at less likely. This gives us our final, most stable policy gradient update. Look at this beautiful formula. The gradient of j of theta is the expectation of the sum of our log probabilities multiplied by the advantage. We are no longer reinforcing raw scores. We are reinforcing positive or negative surprise. This is a huge improvement. But it raises a new question. How do we get v of st? We don't know the true value function. So we learn it. We use a second neural network to approximate it. And this leads us to the famous actor-critic architecture. We have two new characters in our story. First, the actor. This is our policy, the LLM itself. This is the player. Its job is to look at a state, st, and decide on an action, at. It learns using the policy gradient we just saw, driven by that powerful advantage signal. Then we have the critic. This is the judge. It's a second neural network whose only job is to look at a state, st, and estimate its value, v of st. It learns by simply trying to match its prediction to the actual reward it sees later, a simple mean-squared error loss. Here's the full actor-critic loop. You can see the diagram here. The state goes to both the actor and the critic. The actor takes an action in the environment, the critic predicts a value, the environment gives back a real reward, we use the real reward and the predicted value to calculate the advantage, that advantage is then used to update the actor. And the difference between the reward and the predicted value is used to update the trend. They learn together in a beautiful feedback loop. Now in practice, for LLM-S, the actor and critic aren't totally separate networks. That would be inefficient. Instead, the critic is just a tiny value head tacked onto the end of the main transformer. It's incredibly efficient because both the player and the judge are learning from the same deep understanding of the text. Okay, let's connect this back to our haiku. Remember, the LLM generated the full response and got a final reward of r equals 0.9. Now, let's zoom in on the moment the LLM is about to prevent the final word, awake. Here's what happens in an actor-critic setup. Step 1. The actor, which is the LLM, suggests the action at equals awake. Step 2. The critic, our new value head, looks at the state of the text so far and predicts the expected reward from this point. It says, I think the value v of st is about 0.85. Step 3. The environment, our reward model, gives the actual final reward for the whole haiku, which is r equals 0.9. Step 4. The advantage is calculated. A equals r minus v of st. which is 0.9 minus 0.85, which equals positive 0.05. Do you see the difference? We are no longer giving a massive times 0.9 reward, a huge, noisy signal. We're giving a precise times 0.05 signal, a small, positive surprise, a gentle nudge in the right direction. By introducing a learned baseline, actor-critic methods provide a stable and efficient learning signal, finally solving the high-variance problem of reinforce. Our learning signal is now clean and precise, but in doing so, we've created a new, more dangerous risk: instability. What happens if our actor-critic model encounters a batch of data with an unusually high advantage? It will take a massive gradient step. A step so large it could completely destroy the policy, leading to a catastrophic collapse. The model forgets everything it knew in a single update. This is the final boss we have to defeat. And the algorithm that does it is the modern standard for LLM alignment: Proximal Policy Optimization, or PPO for short. So what's the core problem here? We're trusting the gradient too much, and this is especially dangerous for LLMs. Imagine an LLM finds a specific phrase that triggers a high reward from the reward model. What does it do? It chases that signal aggressively, abandoning grammar, abandoning coherence, just to get that reward. This is reward hacking. We want to improve our policy, of course we do, but we need a safety harness. We need to stay within a trust region of our current capabilities. So the core question PPO answers is this: how can we take the biggest possible improvement step without risking a catastrophic performance drop? Now, older algorithms used really complex, heavy math to solve this, but PPO's genius is a much simpler trick: a clipped surrogate objective function. Let's break it down. Part 1, the probability ratio. First, we just need to know how much our policy has changed. We use the ratio r sub t of theta for this. Now look at this formula. It's just the probability of an action under our new updating policy, that's pi sub theta, divided by the probability under a frozen old policy, pi sub theta old. If r sub t is greater than 1, the action is now more likely. If r sub t is less than 1, it's less likely. Simple as that. Okay, here is the full PPO clipped objective. I know it looks a little scary, but don't worry about the whole thing. The most important part of this entire formula is that min function right in the middle. Let's look at the two cases that matter. Case 1. The advantage a sub t is positive. We found a good action. The objective becomes the minimum of two things: r sub t times a sub t, or 1 plus epsilon times a sub t. This creates a ceiling. Once our ratio gets bigger than 1 plus epsilon, the objective goes totally flat. There is no more incentive to get too greedy. Case 2. The advantage a sub t is negative, a bad action. Now the objective becomes the minimum of r sub t times a sub t, or 1 minus epsilon times a sub t. This creates a floor. Once the ratio drops below 1 minus epsilon, the objective goes flat again. The model isn't punished too severely. It prevents us from overreacting to a mistake. This simple clipping mechanism is the safety harness. It allows for steady, consistent improvement while aggressively preventing any single update from destroying the model. But for large language models, we need one last thing: the final safety belt, the KL divergence penalty. To make the system even more robust, a penalty is added to the loss function. You can see the formula here. The final loss is our L-clip objective, minus a new term, beta times KL of pi theta old and pi theta. The KL term simply measures how much our new policy has diverged from the original one, which is often the original fine-tuned model. The beta term just controls how heavily we penalize that divergence. This KL penalty is the ultimate safety belt. It ensures the LLM doesn't forget the grammar, the knowledge, and the style from its initial training just to chase a reward. By combining the stable updates from an actor-critic framework with the safety of a clipped trust region objective, PPO provides the robust algorithm needed to align massive LLMs.
We've built the entire stack. We've gone from a fundamental problem all the way to the state-of-the-art algorithm. This entire video can be summarized in 4 essential steps. Let's walk through this journey one last time. You can see it laid out right here. First, step 1.
We started with the core challenge. You can't use standard gradient descent to optimize for a black box reward. You just can't backpropagate through something like a human's opinion. Second, the log derivative trick broke through that wall and gave us reinforce, but its learning signal was incredibly noisy due to high variance. It was a start, but it wasn't stable. Third, a baseline cut through all that noise. This led to the actor-critic architecture, which gave us dramatically improved stability. Now, we were getting somewhere. And finally, step 4. PPO's clipped objective created a trust region, a safety harness, preventing the policy from destroying itself with a bad update. Now, why does all of this matter? When you hear about companies using RLHF, reinforcement learning from human feedback, this is the machinery at work. It's this exact process. 1. They collect human preference data to train a reward model. That's our black box R. 2. Then, they use that reward model inside a PPO loop to update their base LLM. That's our actor, pi sub theta. And 3. All the while, a crucial KL penalty acts as a safety belt, ensuring the model doesn't forget its core knowledge. And while the scale is immense, the core algorithmic principles behind the alignment of the most advanced AI models are exactly what you have learned in this video.